Okay, so rate of radioactive decay. I'm going to, I forgot one problem, so I just wrote it out here. And I've written out all the problems. I've done the calculations completely, so I'm just going to run through them to save some time, because there's a lot of different forms here. But before we get started, we have to talk about the activity of a nuclear sample, and it's registered as curies. One curie is 3.7 times 10 to the 10th disintegrations per second. So because that's, you can see how large this number is, so it's often easier to work in curies than to talk about how many disintegrations you have per second. So we're going to have to go back and forth between those two sets of units. So if you have 3.13 milligrams sample of technetium-99 and it has an activity of 25 curies, what is the decay constant? So here's our equation that we use. Rate is nuclear disintegrations per second, that then we can relate back to curies. The decay constant is here, K, and then N is the number of nuclei that are available to decay at a certain time. So if we look at the units, we have rate is nuclei per second that are decaying. I have it as nukes, but NUC per second. Inverted seconds, and then nuclei. And as you can see, that this is disintegrations, that's also just nukes per second. And so you can relate these units to curies. So we have, but first thing is figure out how many nuclei you have. We're assuming that we have a pure sample here. That's can be a good approximation, maybe not, but in this case we're going to assume we have nothing but the technetium-99. So we have this many grams of it. I converted the milligrams over. Now, what's the mass of the technetium-99? Well, it's right in the name. It's 99, so we use that. We don't use what's in the book, in the periodic table. It might match up, it might not, but we're talking about certain types of nuclei. So even though carbon has, for its mass, or its atomic mass in the periodic table says it's 12.01. If we're dealing with nothing but carbon-14, then it's 14. So you got to keep that in mind. Change to moles, change to nuclei. Here's our nuclei. Now, so this is our N of T right here. Then we have to convert to, since we're in nuclei here, and we have nuclei here, we have to change the curies to nuclei per second. So 25 curies, one curie is this many nukes per second. Here's so this is now our rate. When it's in curies, we call it an activity. When we're in nuclei disintegrating per second, then it's a rate. Now we put everything in, and we solve for K. And this should look very, very familiar. We did this in our very first chapter. And nuclear decays are always first order. So unlike in that chapter where we were talking about chemical rates, we had 0th, 1st, and 2nd. We always, this is such a bad always, we'll always be dealing with first order. So that we only have to deal with 1/3 of the equations that we had from that chapter. But the same equations work. We just call them, and we call this the nuclear decay constant rather than the rate constant. We just make little changes like that. Okay, so that was the one equation problem that I left off. Here, so the rest of these are printed up. So the decay constant for a certain isotope is 6.15 times 10 to the minus 6. So 10 to the minus 6 inverted seconds. So that's our K. Inverted seconds, so that's our K. What is the half-life? Now the equation, we take it straight from that the chapter that we had long ago. The half-life for a first-order reaction is equal to 0.693 over K. So if you know K, you know the half-life. If you know the half-life, you know K. Now, I've asked for it in days, because when you have a half-life that's 1.13 times 10 to the 5 seconds, that doesn't give you as much information. The half-life tells us, as you might recall from the first chapter that we did in this semester, that the half-life indicates how long before half of the nuclei are gone. So, well, that doesn't, for me, that doesn't tell me anything. 1.3 days, yeah, that tells me that in a week, it's essentially all going to be gone, or going to be down to just a few percent. So I get a pretty good idea compared to this. So if I were working with this substance, I know that I probably only have a few days, 2 or 3 days to work with it before it's going to be, so much of it will be gone that I won't have much to work with, enough to work with or to get data from. So the half-life of a certain isotope is 3.515 days. What is the decay constant for this isotope? Now normally, decay constant, just like we used way back when, is in inverted seconds. If I don't state that, then you can leave this as 3.15 days, and then your decay constant will be in inverted days. Not the end of the world. That's certainly something that can be used, but normally, what I'll say is that the decay constant should be in inverted seconds. So just rearrange the equation, and we're plugging in numbers. We're doing exactly what we did, back in the first chapter. Now, now this is where things start to change for us. The half-life of vanadium-53 is found to be 0.015 seconds. What is the decay constant for this isotope, and what is the activity of 0.5 grams of this isotope? So this is kind of the reverse of that first problem that we did. So the first thing is determine what K is. That's what they want, the decay constant. So just plug it into this equation. Rearrange this equation into this form, and here's our K. So this is our first answer. Now they want the activity, so we need to find the rate first and then convert to Curies. Well, we know the K, so we know this guy now. They give us 0.5 grams of the isotope for vanadium-53. So you have to run through 0.5 grams, 53 grams per, I shortened it up here, it's 53 grams per mole. 1 mole is 6.02 times 10 to the 23rd nuclei. So here's our nuclei, so that goes here. And then we convert to nuclei per second, and say nukes per second, but it's really nuclear disintegrations per second. So you want to reduce this down to this form, just save yourself some writing. So we got a lot of nuclei. We should, because it's 0.5 grams. That's a lot, and so we should expect to see a large number here. But then we want to convert to Curies. We have this many nuclei per second that are reacting. Or are decaying, I should say. And then we have 1 Curie, it's 3.7 times 10 to the 10th nuclei per second. These cancel. We're left with a very high activity. That's extremely high, but that's because I made this number really fairly large. We usually deal with milligrams or micrograms, and then I made this half-life extremely short. Normally we're dealing with half-lives that are on the order of months or years or even millions or billions of years. So this shouldn't be too surprising, though I'm going to go really quick since I'm doing this just to make sure. Because when I did it the first time I said, man, that's large, but it seems to be accounted for. This guy is very large. This is generally going to be, should be like, for most isotopes that we're going to deal with, 10 to the minus 7, 10 to the minus 8th. So this is, yeah, it makes perfect sense as far as, can't guarantee I guess I can finish it up since I'm doing this. Yeah, so that's where we get, because our Ks, most of the Ks you're going to see are going to be much smaller than that. Okay, the half-life of a certain isotope is 15.6 days. What fraction of a sample of this isotope is left after 45 days? Okay, so this is where we take a tremendous break from chapter 13, I believe it was. We're not looking for NT or N0, we're looking for the fraction. Well, I think we did something along this line back then. But here we're going to get rid of the rate constant by noting that the K is equal to 0.693 over the half-life and plugging that in. So we get rid of the rate constant since we know there's a relationship between the rate constant and the half-life. And since they gave us this in terms of half-life, and in nuclear decays, that's almost exclusively what you'll be dealing with, is the half-life. So they give us the half-life in days, And so we know that's going to go here. They want to know how much of the isotope is left in 45 days, so there's no reason to change units of measure. Because if you did that, if you change this to seconds, you'd have to change this to seconds. So leave it in the same units. And then you solve for the ratio. And this is, you have 13.5% left. And that's what they're asking for. But they could also ask how much was used up, which is this one. This is what confuses students. They get this as their answer, but that's not what they're asking. They're not asking how much is left. They're asking how much was used up, so be careful there. And notice we don't state at all how much we started with. It could have been a little bit, you know, that would fit on the head of a pin, or it could be something that fills a room. They don't state, because by first order we don't need to know how much for the half-life. If you remember, for second order and zeroth order, we needed, back in the chapter 13, we need to know the concentration of the chemical that we were dealing with. Here, we don't deal with concentrations first off, and we never deal with zeroth or second order rate laws. So don't have to know what we started with. Whatever we started with, we have 13.5% left, or, yeah, there it is, or 0.135 for the ratio. Alright, so we have the desiccated nose of a caveman is found to emit 3.8 disintegrations per minute per gram of total carbon. Now when we're doing carbon dating like this, we need to have a piece of matter that was living at one time. So I just picked the nose. This caveman had a hard time at some time in the past, and we want to figure out how long ago it was. Well, all living matter gives off this rate of disintegration per minute per gram for the carbon. So all living things, trees and plants and animals, fish, birds, insects, everything that's alive that has carbon in it is giving off this amount of radiation at that rate. After it dies, then it's no longer taking in carbon-14. I should make that point. We're dealing with carbon-14 dating. So the carbon-14 is the thing that's giving off this radiation, and after something dies, it no longer is ingesting things that contain carbon-14, and that's the only way that it's going to, they're going to intake the carbon-14. Plants will bring that in photosynthesis. So the carbon-14 that's left starts to decay, or it keeps decaying, but there's nothing replacing it. So we can tell from the amount of radiation that it's giving off how old the thing is. So we have what we do. This is supposed to be nuclei. These are both supposed to be nuclei, but we can relate the amount of disintegrations is directly proportional to the number of nuclei. So we're using the wrong units here. This should be nuclei, but that's okay. We're using nuclear disintegrations per minute per gram. As long as there's a direct relationship between the disintegrations that we see per minute per gram and the actual number of nuclei, which there is, then we're all set. So these cancel. The half-life is 5,730 years, and I'd give that on the exam. It's usually right in the problem because I can never remember it. It's and actually, I think in some books I've seen it as, let me just verify here. Yeah, so 5730, just make sure I got it right there. I've seen different numbers for this, just the last digit or so. And so I'll give that to you. But you need to know the equation, and you solve for t. And I don't even worry about the significant figures here, just leave it as is. So 11,517 years ago, the caveman lost his nose. Okay, so that is it. Those are the types of calculations that you'll be working with.